Okay, today we are going to learn slopes of tangents and instantaneous rate of change. This is lesson 8 of unit 4. First, let's have a look at today's learning goals. So after today's lesson, you should be able to understand that an instantaneous rate of change corresponds to the slope of a tangent to a point on the curve. Find the equation of the tangent line, aka the instantaneous rate of change at any given point given the expression of a function. Find the slope of the tangent line or instantaneous rate of change at a specific point given the expression of a function. Estimate the slope of the tangent line or instantaneous rate of change at a specific point using approximation given a graph or a table of values of a function, and then solve real-world problems involving instantaneous rate of change. Okay, so first of all, let's have a look at the concept of the slopes of tangents and instantaneous rate of change. So suppose we have a function fx and the graph of fx is sketched on the left. And then we have two arbitrary adjacent points, P, x, fx, and q, x plus h, and fx plus h. So that means the x coordinate of P is x, and the x coordinate of Q is x plus h, right? And we already know that the slope of the secant between P and Q is given by the following formula here, which is delta y over delta x, right? Delta y is the difference between the y coordinates between these 2 points, and delta x is the difference between their x coordinates, which can be simplified to fx plus h minus fx over h, right? Of course, h is not 0. So note here, when h approaches 0, then delta y over delta x will approach the slope of the tangent line at P, right? So as you imagine, when Q is very close to when Q is very close to P, that means when h approaches 0, the slope of the secant line will approach the slope of the tangent line at point P, right? Which is also the instantaneous rate of change of fx at point P, which is also denoted as the limit as h approaches 0 of fx plus h minus fx over h, or we also denote it as the first derivative of fx, or dy over dx. Okay, I put a special note here. This concept is only applicable when the limit is defined at point P, which is not always true. You will explore deeper in the course MCV4U, that is Calculus and Vectors, grade 12. For now, we only consider the cases where such limit exists. Understand? So let's make a summary. We have 2 adjacent points along the curve, and when h approaches 0, the slope of the secant line will approach the slope of the tangent line at P, right? Which can be calculated as a limit as h approaches 0 of f plus h of x plus h minus fx over h, which can also be denoted as the first derivative of fx, or dy over dx. Okay, so let's use some example questions to illustrate this concept. First, let's have a look at a question that involves finding the equation of the tangent line or instantaneous rate of change at any given point, given the expression of the function. So suppose we have a function fx equals 2x squared plus 3. The question is to find the equation of the tangent line at any given point, x, fx, on fx. Okay, so I'll give you 5 minutes to think about this question. Okay, let's have a look at the solutions together. So according to the definition of instantaneous rate of change, the slope of the tangent line or instantaneous rate of change at any point x fx on fx is given by this limit, right? The limit as h approaches 0, the difference between f of x plus h minus fx over h, right? So first of all, let's have a look at what is f of x plus h. We can simply plug x plus h into the expression of fx, which is twice of x plus h squared plus 3. And then what is fx? Fx is simply 2x squared plus 3 over h, right? The limit as h approaches 0, which is the limit as h approaches 0. Then we can simplify the numerator first. The numerator is 2x squared plus 4xh plus 2h squared plus 3 minus 2x squared plus 3 over h, right? And this is the limit as h approaches 0. And the numerator now is simplified to 4xh plus 4h squared over h, which is the limit as h approaches 0. Note that h approaches 0, but h is not 0, right? So we can cancel an h here, which is 4x plus 2h. So that means when h approaches 0, 2h should also approach 0, right? And the limit of 4x plus 2h is just 4x, right? So this is our final result. Therefore, the slope of the tangent line at point x fx is 4x, right? You can also check the complete solution on this lecture slides if you like after the class, all right? Okay, so please have a look at the solution and let me know if you have any questions. Okay, let's have a look at another example. Example 2 is about to find the slope of a tangent line or instantaneous rate of change at a specific point, given the expression of a function. So now this time we have a function fx equals x squared minus 4x plus 3, which is a quadratic function, right? And the problem is to find the instantaneous rate of change at the x-intercepts of fx. Okay, I'll give you 10 minutes to think about this question first. Okay, let's have a look at the solutions together. Actually, there are two methods to solve such a problem, right? So method one is we can evaluate the slope of the tangent line at any given point x fx, right? And then if we find the equation of the tangent line, we can then put the x coordinates of the x-intercept of fx into that equation to get the slope at that specific points, right? So let's have a look at method one. First, find the equation of the instantaneous rate of change at any given point fx. Let's say at the point here, the instantaneous rate of change, according to the definition, is a limit as h approaches 0, the ratio between fx plus h minus f of x over h, right? So first of all, we need to evaluate f of x plus h, which is x plus h squared minus 4 times x plus h plus 3, and then subtracted by fx. fx is x squared minus 4x plus 3, right? All right, do not forget the limit sign, which is a limit as h approaches 0. The numerator can be simplified to 2xh plus 2h squared minus 4h. Note that some terms are canceled, right, over h. And because h is not 0, that means we can cancel an h here, which is limit of the limit as h approaches 0 of 2x plus 2h minus 4, right? Which is as h approaches 0, 2h is also 0, which is 2x minus 4, right? So the instantaneous rate of change at any given point x fx is 2x minus 4, right? Then we can just put the x coordinate of the x-intercept of x into this equation to get the instantaneous rate of change at that specific point. So we note that fx equals, we can factor fx to x minus 1 times x minus 3, right? So the x-intercepts are 1, 0, and 3, 0, right? And at the point 1, 0, the instantaneous rate of change is 2x minus 4. Then we can put x being 1 into this equation, which is 2 by 1 minus 4, which is minus 2, right? And at the other point, 3, 0, the instantaneous rate of change equals 2x minus 4, and this time x is 3, so 2 by 3 minus 4, which is 2, right? Okay, so please have a look at method 1 and let me know if you have any questions. All right, so there is another method which we can evaluate the instantaneous rate of change at each of the specific points directly. So for example, first we need to find the zeros of fx, right? To find zeros, to find the x-intercept of fx, we can use this method here to factor fx into x minus 1 times x minus 3. And then the x-intercept is 1, 0, and 3, 0. I'm not gonna write it here, okay? And then at x-intercept 1, 0, we can directly evaluate the instantaneous rate of change at this point, which is the limit as h approaches 0 of f1 plus h minus f1, right? Over 1 plus h minus 1, which is actually h, right? Next, this is limit as h approaches 0. First, f of 1 plus h is 1 plus h squared minus 4x. 4x is 4 times 1 plus h, then plus 3. Then f1. f1 is 1 squared minus 4 by 1 plus 3, right? Over h. And then the numerator can be simplified to 2h plus h squared minus 4h, right? Over h, which is a limit as h approaches 0 of 2 plus h minus 4, right? So as you can see here, as h approaches 0, 2 plus h minus 4 is minus 2. So in this way, we directly evaluated the instantaneous rate of change at 0.10, which is minus 2, right? So using the same method, we can also evaluate the instantaneous rate of change at the other x-intercept, which is 3, 0. So I'm not going to write it here, okay? You can check the complete solution of method 1 or method 2 in these lecture slides after the class, okay? You can choose either way to find the instantaneous rate of change at any given points. So to this specific problem, because we're going to evaluate the instantaneous rate of change at 2 points, so I think method 1 seems a little bit easier, right? Because once you have the equation of the instantaneous rate of change at any given point, you can just simply put the coordinate of any point into that equation to find the instantaneous rate of change at that given point. So for example, if you want to evaluate the instantaneous rate of change at 4 different points, then you can just plug the coordinates of the 4 different points into that equation to find that instantaneous rate of change at those specific points, right? It is much easier than you use method 2, because in method 2, each time you evaluate at different point, you're going to evaluate the limits. You're going to go through all the process again and again, okay? So I think method 1 is much easier for this kind of problem. Okay, next, let's have a look at another example question. This time, we are given a graph of a function, and we are expected to estimate the slope of the tangent line, or instantaneous rate of change, at a specific point using approximation. So sometimes it is not possible, or it is not very easy to find the exact solution. So we can also use approximation to find a approximate slope of the tangent line at a given point. So the question states that the graph shows the approximate distance traveled by a parachutist in the first 5 seconds after jumping out of a helicopter. The question is, how fast was the parachutist traveling 2 seconds after jumping out of the helicopter? So this means we want to find the instantaneous speed at t equals 2 seconds, right? Which is a instantaneous rate of change of distance with respect to time t, right? Okay, so I'll give you 5 minutes to think about this question first. Okay, let's have a look at the solution. So the parachutist velocity at 2 seconds corresponds to the instantaneous rate of change at t equals 2 seconds, right? Therefore, calculate an approximate value for the instantaneous rate of change is how we can solve this problem, right? So we can let P be the point on the graph at t equals 2 seconds. So P is here, and determine the slope of the secant passing through P and another point on the curve that is very close to P. So we can select the point Q, 3:45, which is close to P and easy to read from the graph, which is here, right? The reason we select Q here is because this is a closest point from P whose coordinates is easier to read. For example, if we choose this point, the y coordinate is not very clear to us, right? So we choose Q here. And then the slope of the secant PQ is given by MPQ equals delta D over delta T, which is 45 minus 20 over 3 minus 2, which is 25, right? So this is an approximation of the tangent line at point P. This is the best result we can get from the graph, okay? So this time, it's not very easy to find the exact solution, but instead we can approximate the slope of the tangent line using the slope of the secant line, as long as Q is not very far from point P. The result is acceptable. So using a secant line, the parachutist velocity after falling for 2 seconds is approximately 25 meters per second. Okay, so please have a look at the solution here and let me know if you have any questions. All right, if not, let's have a look at another example problem. Given a table of values of a function, estimate the slope of a tangent line, instantaneous rate of change at a specific point using approximation. Okay, this problem states that in the following table, the distance of the parachutist in example 3, which is the previous example, is recorded at 0.5 seconds intervals. Estimate the parachutist velocity at 2 seconds. Again, we're going to calculate the instantaneous rate of change of D in terms of T at T equals 2 seconds, which is here. You need to find the instantaneous speed at T equals 2 seconds, right? And sometimes it is not very easy to find the expression of the function, which is the case in this example. But if you are given a table of values of a function, it is possible to approximately evaluate the instantaneous rate of change at a given point. Okay, again, this time we're using approximation. Okay, so I'll give you 5 minutes to think about this problem by yourself. What is the estimated instantaneous speed at t equals 2 seconds? All right, let's have a look at the solutions together. To estimate the instantaneous rate of change from a table, calculate the average rate of change over a short interval by using points in the table that are closest to the tangent point. The table shows that at 2 seconds here, the parachutist has traveled a distance of 20 meters. A point that is close to 220 is a point 2.5, 31.25. So we can choose this point, which is adjacent point to 2.0. The average rate of change between 220 and 2.5, 31.25 is delta t over delta t, delta d over delta t, right? Delta d is, according to the table, 31.25 minus 20, and delta t is 2.5 minus 2, which is 11.25 over 0.5, which is 22.5. The unit is meters per second. Therefore, the parachutist velocity at 2 seconds is approximately 22.5 meters per second, right? Notice that we can also choose the point 1.5, 11.25 as the closest adjacent to the given point. You can choose either point, right? Okay, so please have a look at the solution here and let me know if you have any questions. All right, let's have a look at another example problem. This time we have a real-world problem that involves the instantaneous rate of change. Alice is traveling according to the equation s equals t cubed minus 6t squared plus 9t plus 1, where s is a displacement in meters and t is the time in seconds, and t equals or greater than 0. What is her velocity after 3 seconds? So it asks us to find the instantaneous velocity at t equals 3 seconds. Okay, so I'll give you 10 minutes to think about this question first. Okay, let's have a look at the solutions together. So her velocity at t equals 3 seconds is instantaneous rate of change of s with respect to t at t equals 3 seconds, which is the limit as h approaches 0 of s3 plus h minus s3. So this time we directly evaluate the instantaneous rate of change at t equals 3. So we can use this limit, which is limit as h approaches 0 of 3 plus h cubed minus 6 times 3 plus h squared minus 9 3 plus h plus 1 minus 3 cubed minus 6 times 3 squared plus 9 times 3 plus 1, right? This is all numerator divided by h, which is limit as h approaches 0. Now the numerator becomes h, 3 plus h squared plus 3 plus h plus times 3 plus 9 minus, we can put 6 in front, and 3 plus h plus 3 times 3 plus h minus 3, then plus 9h over h, right? And this is a limit as h approaches 0 of h times 9 plus 6h plus h squared plus 9 plus 3h plus 9 minus 6h, h plus 6 plus 9h over h, right? So as h is not 0, so this is a limit as h approaches 0, we can just cancel the h here, right? This is actually 9 plus 6h plus h squared plus 9 plus 3h plus 9 minus 6 times h plus 6 plus 9. And as h approaches 0, we can see that this is 0, this is 0, and this is 0, and this is 6, right? So the limit of this expression is 9 plus 9 plus 9 minus 36 plus 9, which is 0 minutes per seconds, meters per seconds. Therefore, her instantaneous velocity at t equals 3 seconds is 0 meters per second, right? You can also check the solution, the complete solution on this lecture slides, if you like, after the class, okay? All right, so please have a look at the solution here and let me know if you have any questions. Right, so this is what we have learned so far. And let's make a summary of today's lesson. So after today's lesson, now you should be able to understand that a instantaneous rate of change corresponds to the slope of a tangent to a point on the curve. Then find the equation of the tangent line or instantaneous rate of change at any given point given the expression of a function. And find the slope of the tangent line or instantaneous rate of change at a specific point given the expression of a function. Estimate the slope of the tangent line or instantaneous rate of change at a specific point using approximation given a graph or a table of values of a function. And last, solve real-world problems that involve instantaneous rate of change. Okay, so the rest of the time is reserved for you to complete today's homework. So remember to submit it before, remember to submit them before the deadline, okay? And if you finished, also remember that there is a final project in this course. So you can also start doing your final project, and do remember to submit the final project onto Google Classroom before the end of the class, okay?